Hi there, everyone. Welcome back to Elementary Statistics. The last time I saw you in class, we had barely started on Chapter 12. And for this first video lecture, I've made the executive decision to skip over the remainder of Chapter 12. It's really interesting material, and so I'm a little sad to be doing that. But there is more relevant content that we would like to get through before the end of the semester. So we're jumping right into Chapter 13, and today's video is going to talk you through the important content in Chapter 13.1. Remember that after watching this video, there will be a live session on Tuesday the 24th. Your regular class time will be for that live session, except we'll start with a 20-minute delay in case anyone is only watching this video right at the start of class. So my timing is allowing for that. And when you sign on to that live session at 2:20 Central Time, I will be working through some examples for section 13.1, and that entire session will also be recorded and the video will be posted. So if you are unable to attend live, you will not be missing out on any of that content. Now, let's look at section 13.1, which is going to emphasize a new concept to us. We're going to define what I will refer to as the sampling distribution. And we're specifically going to do this in the context of the proportion of a sample that satisfies a certain criteria. And I know that sounds a little bit ethereal, so let's get real. Because what is more important and more fun than talking about M&Ms? So let's consider this hypothetical scenario where I have a bag of M&Ms, standard bag, like individual size, not family size bag, but individual size bag of M&Ms contains typically 57 pieces. Let's assume I have one of these bags. I really mix up the pieces well, and I randomly draw out 5 of those pieces. And I want to consider what proportion of the M&Ms in the sample of 5 are red. So a lot of different things could happen, right? We've talked about randomness. We know that each time we take a sample, it will have slightly different behavior. And so let's look at a few hypothetical samples. My first sample that I take, I could imagine that my first M&M is red, followed by a green, a blue, a green again, and finally a red. So in this specific sample, 2 of the 5, or 40% of my M&Ms are red. I could, of course, have taken a completely different sample. I could have gotten a green, a yellow, and finally a red, which in this case would mean 1 of the 5, or 20% of my sample, would be red. Or finally, depending on, again, randomness, luck of the draw, if you really value red M&Ms, it is certainly not impossible that you take a sample and all 5 of them are red. So in this case, my proportion would be 100%. So a lot of different things could happen when I take a sample of M&Ms. Each of these samples is a plausible outcome. They may not all be equally likely, but all of them could happen. Now, a nice thought exercise would be to think through how many possible samples could I take, right? A bag with 57 M&Ms, taking out 5, you may think, well, there aren't that many ways in which I could take a sample. And if that's your first instinct, I have bad news for you, because there is nearly 4.2 million different samples of 5 M&Ms that you could take out of a bag of 57. But if we could take all of these samples, and for each sample, I calculate what proportion of the M&Ms are red, and I then draw a histogram, what I would see is a histogram similar to the one displayed below. So what you'll notice is the modal outcome, the most likely outcome in this case would be 20%. So 2 of the 5 M&Ms being red. But it could be that in some samples we have 0. It could be that we have 100, but you'll see here the bar at 100 is really, really small. So that becomes a really implausible outcome, not impossible, but highly unlikely. So this graph that you're seeing, this histogram, this is referred to as the sampling distribution. Let's unpack that a little bit more. In this specific example, we are calculating the percentage of red M&Ms in a sample, and that is called our statistic. So we're taking 5 M&Ms out of the bag randomly. Those 5, they represent our sample. The full bag of 57 would be our population. And so in a population of 57, we're taking a sample of size 5, and we are then calculating in our sample what proportion or what percentage of the sample is red. So we could do this repeatedly. Again, if you'll remember, a few slides ago, I tabulated different possible outcomes, and each of those corresponded to a different value of the statistic, or a different value for the percentage red. So if I talk about the sampling distribution, I am referring to 2 quantities jointly. I'm talking about the collection of all possible values of the statistic. So in this specific example, there are 6 possible values, right? I could have 0%, 20%, 40%, 60%, 80%, or 100% red. Those are the possible values for my statistic. And knowing how frequently each of them occurs, or what percentage of times those values occur, that together with the values, we call the sampling distribution. And it will often be visualized in something like the histogram. So just to take this M&M example a little bit further, and I know you're all really checking your pantries right now to see if you have a bag of M&Ms there. If you want to hit pause and you want to go and get a snack of M&Ms, please be my guest. But I am moving on here without a break. Oh, yes, I am suffering for you and going without M&Ms. So I could have done this experiment a little bit differently. I could have said, well, I still have a bag with 57 M&Ms, but instead of taking out 5, I'm taking out 13. And now you see there are a lot more values that are possible for percentage of red M&Ms, ranging from 0% to, like, the largest value here is, it's not quite 70%, but it's pretty close. And I could go even in a different direction and say, well, I'm not going to take 13 M&Ms out of the bag. Maybe I'm going to take 22 M&Ms out of the bag. Where from the 5 or the 13 or the 22, those just represent sample sizes, right? In real life, when you're collecting data, you will be able to obtain a specific sample size. And so I'm just illustrating the concept here with a few different sample sizes. But what you should see is the larger we make the sample size, if we look at this histogram, the larger the sample size, the more you should start seeing something that resembles that familiar bell curve. So M&Ms are fun to talk about, but let's get into a real world example. The National Center for Health Statistics in the year 1998 managed to monitor every single live birth in the US. There were nearly 4 million live births, and what they found when tracking these is that 11.6% of those corresponded to premature births. Now, this may represent what they saw in 1998. 1999 would not necessarily be very different, but you can't track every single live birth every year and do a comprehensive exam on every child that is born. So the way we can think of 1999 is saying, oh, we're just going to sample 100 births and do comprehensive exams of those newborns to see what percentage of them are underweight. So this is almost the same as taking our 1998 data and drawing a sample of size 100. Now, you'll remember from a few minutes ago when we were talking about the M&Ms, I said if we look at how many ways we can take a sample of size 5 out of a population of 57, we had more than 4 million such samples. Now we're looking at a population of nearly 4 million and thinking through how many samples of size 100 we can draw. That number is astronomical. Like, it has so many zeros, I'm not even going to try and write it down here. It is impossible to take every single conceivable sample of size 100. But we can draw a few thousand samples, and that is then an approximation to our sampling distribution. So if you think through this, let's say I have these nearly 4 million births, and I go and take a sample of 100, I may find that in one particular sample, 12% of newborns are underweight. In another particular sample, 10% are underweight. I could take a third sample of 100 and find 16% are underweight. And I could do this repeatedly over and over again. And eventually, if I draw a histogram of all these sample proportions, I'll get an image similar to the histogram on the present slide. Now, what you should notice here is our sample size at this point has gotten reasonably large, right? Sample size of 100 that we're drawing from the population. And so the resulting histogram with all the possible proportions is nearly symmetric, and it's nice and unimodal. And if we look at it, we know the true value in the population is 11.6%. This histogram here is very nearly centered at that 11.6%. We can also calculate the standard deviation, and in this specific example, the standard deviation is 3.2%. Now, the assumption that we are going to make when working with the sample proportion going forward is we will assume that a normal distribution is a reasonable assumption to make. So the normal model that we've spent a lot of time talking about, we are going to apply the normal model to that. Now, what does the normal model say? If the sample proportion follows a normal model, that tells you that samples are going to differ from one another, and they will not all have the same value for the proportion. There's going to be variability from one sample to the next. But using the normal model, that allows us to quantify how much variation there is. And if we can quantify the variation, then the information that we observe in the sample, we're actually able to use that and make statements about the population. So developing the normal model allows us to better understand how a proportion here operates and how we can then apply it. So when we apply a normal model in the context of a proportion, we specifically know that the population mean, or the mean of that normal model, gets denoted by P. So remember, P is our proportion. The P by itself represents the true proportion in the population. The sample proportion will denote by P hat. So the hat tells us it's a quantity from the sample, it's a sample statistic versus a population parameter. So the P without a hat is a parameter, the P with a hat is a statistic. Most of the time, the statistic is what we're able to observe because that's what we get from our sample. But the P without a hat, that is of interest to us, but we can never or generally, we have a hard time taking a full census. And so we can't observe the true P, but we can use P hat to learn about P. And the quantity that tells us how close those typically are to one another is the standard deviation of our model. And in this instance, sigma is a usual symbol that we use for standard deviation. And to emphasize that it's referring to the proportion, we're going to say sigma of P hat, put that in parentheses. You could also write it SD for standard deviation of P hat. And the way you calculate this quantity, the standard deviation for this normal model is given by P times Q over N, square root of that entire quantity. So P, you already know, is the true proportion. But in addition to that, Q is just 1 minus P. And N, of course, denotes the sample size. And you just plug the values into that formula, and tomorrow I'll walk you through a few examples of that. But let's implement it one time. So in the specific birth weight example, we know P is equal to 0.116, which means Q is 1 minus that value, which in this specific instance would be 0.884. And finally, N, our sample size, is 100. So we know what the standard deviation of the sample proportion is. It's given by 0.116 times 0.884 over 100, and then you take the square root. If you go and do this calculation, you'll get 0.032, which is the same as 3.2%. So how does this then fit back into our normal model? Well, normal model tells us bell curve, right? And bell curve tells us we are centered at P, and then remember that 68, 95, 99.7 rule, that tells us if we're moving to the right, we add 1 and then 2 and then 3 standard deviations, or if we're moving to the left, we subtract 1, 2, or 3 standard deviations. So in this specific example, we know our population mean is 11.6%. We know our standard deviation is 3.2%. So our normal model is a bell curve centered at 11.6. And then if we add 1 standard deviation, we have 14.8%. If we add another standard deviation, we have 18%. And adding 1 more standard deviation, we have 21.2%. And if we subtract, we respectively get 8.4%, 5.2%, and 2%. So what this tells us is if the true population consists of a proportion of 11.6%, and we take a sample of size 100, then realistically, remember the true population value is 11.6%, but in our sample, it would be realistic to have anything from 2% all the way to 21.2%. So there's a lot of variability. And we refer to this by the somewhat unfortunate name of sampling error. So the standard deviation of a statistic we call sampling error. But remember, error here does not mean we made a mistake. So perhaps it's more convenient to think about this as the sampling variability. But those two quantities convey the same information. They tell us how much variation we can expect between the true quantity that we're interested in and the value we see in our sample. So remember to tune in relative to when I'm recording this, it's tomorrow, but the 24th at 2:20 p.m., and I'll be working through some examples illustrating this because I know examples really help. So I will talk to all of you tomorrow. Thank you.